Hey, what's up, AP Calc? In this video, we're going to start Chapter 3. Yay! Section 3.1 is pretty short, so I'm just going to go over the first page of this note sheet in the video, and in the next class, we'll just do the problems on the back. So, what Section 3.1 is about is absolute extrema. And sometimes they're referred to as global extrema, so these get used interchangeably. And what they are the largest and smallest values of a function f over the given interval. So here are just four pictures, and we're just going to identify where those absolute maxes and mins occur. So on that first picture, looking for the highest point on that interval, and that would be right here. So that's our absolute max. That would be our absolute min. So why don't you just pause the video and identify those spots on the other three graphs, and then we'll go from there. All right, welcome back, guys. Let's take a quick look here. So I marked up all the pictures. The absolute extrema can occur at the endpoints of the closed interval. So that's what's going on in these first two graphs. In the third one, the absolute max happens to be right here at the top of this hill, and that's the absolute min. And then since these two endpoints have the same height and they're the highest points on the interval, they're both absolute maxes. All right, and then right here at this cusp would be an absolute min. All right, so this is going to take us to this next theorem. Now, on the AP test, there's a couple important theorems that they typically test you on. We already did one of them back in Chapter 1 called the intermediate value theorem. So this would be the next major theorem called the extreme value theorem. And basically says if your function's continuous on this closed interval from A to B, then f has both an absolute maximum and an absolute minimum somewhere on that closed interval. All right, so if you look at those four pictures, these are all continuous functions on the given interval, and they all had an absolute max and an absolute min. That's pretty much what the theorem is saying. Now, notice with this one, there's no condition for differentiability. So if you had like a function that's like a portion of an absolute value graph, even though it's not differentiable at that sharp corner, it still could have an absolute max there. So in that case, this would be an absolute max, and here would be our absolute min. So I'm just going to make a note, differentiability is not a condition of the theorem. All right, cool. So let's go to problem number 1 here. It says identify the absolute extrema on this interval. So since the picture's there, we're just going to identify the spots and name them. So this is clearly the highest point on the interval, so that's our absolute max. This is the lowest point on the interval, that's our absolute min. So we name them. There's two ways we could do this. We could say absolute max of 1 at x equals 0. All right, so that's how we would describe that location. And we could say absolute min of -1 at x equals pi. Now, the shorthand way to do this is just to use function notation. So we could say, or our absolute max is f of 0 equals 1. Our absolute min is f of pi equals -1. All right, but we'll get used to that as we go through this. No big deal there. All right, so the last thing I just want to talk about is what a critical number is. So it's a definition. We're just going to write it down and just ponder it for a second. So the number c is a critical number of a function f whenever f prime of c is 0 or f prime of c is undefined. So just to put that into perspective, we're just going to go back to those pictures at the top. And if you go to that third graph, right in line with that absolute max, I'm just going to put a tick mark and call that C. And that number C that lines up with that point would be a critical number because f prime of C equals 0 for this graph. And we know that because at C, the tangent line's horizontal, so the derivative is 0 there. And then the other thing that would make something a critical number if f prime of C is undefined. So if we go to this graph that has the cusp, we label that spot C. We know that the derivative is undefined at the cusp. It doesn't exist. So this would be an example of f prime of C being undefined. So in those cases, the value of C would be a critical number on the graph. All right, so I'm going to end this video here. Like I said, we're just going to go through those examples on the back in class next time. Won't take us too long. And then we'll review for that Chapter 5 test. All right, talk to you guys soon. Ta-ta.